Hello, my name is Matthew Malone.
And I'm Seyed Seghatoleslam.
We'd like to show you some interesting properties and uses for a peculiar metal known as nitinol. We hope that you'll find it as fascinating as we do. Nitinol, which gets its name from the combination of its components and its place of discovery, is a nearly equiatomic nickel-titanium alloy made at the Naval Ordnance Lab by researchers William Buehler and Frederick Wing. Its original purpose was for use in missile nose cones, but by accident was found to exhibit two very unique properties: the shape memory effect and superelasticity, which is capable of converting mechanical energy into thermal energy. The dominant of the two properties can be chosen during the shape setting process by varying the composition ratio of nickel to titanium within the alloy. A higher concentration of titanium allows the metal to retain its permanent shape at a much higher temperature, while having more nickel will retain this shape at a low temperature. The shape memory effect is a reversible crystalline phase transition, and is demonstrated here in our first experiment, where a straight piece of nitinol wire is crumpled up, clearly undergoing plastic deformation. The wire is then heated to a temperature of at least 40 degrees Celsius for this particular wire, and as you can see, it returns to its original straight shape. What's happening is that the metal is undergoing phase changes between crystalline structures. Originally, the metal's permanent shape is set at 500 degrees Celsius, where its crystal structure is a perfect cubic lattice known as austenite. As the metal cools, this crystal structure relaxes into a crystal structure known as twinned martensite, which is shaped like a bunch of parallelograms stacked in a mirrored pattern. Once in this structure, deformation of the metal results in another phase change to detwinned martensite, where the orientation of the parallelograms are arranged at random. When heat is then applied to the metal, it transitions back to the original austenite structure, undoing any deformation and re-straightening the wire. The permanent shape chosen can have an effect on how this property can be used. For instance, if it's formed into a spring, stretching the spring behaves as expected. But once it's heated, the work done by the spring retracting into its original shape is capable of lifting a considerable amount of weight.
The other property nitinol demonstrates is superelasticity or pseudoelasticity, which is demonstrated here in our second experiment. A straight piece of nitinol wire is bent heavily, up to 30 times that of most normal metals, and is able to snap back in an instant. The mechanism behind this property is similar to shape memory, but instead the temperature at which the metal holds its permanent shape is set below room temperature, so that in normal conditions it's always in the austenite phase. Deformation therefore causes a phase transition to twinned martensite, then detwinned martensite, and once the stress is relieved, it transitions directly back to austenite. And due to the rapid set of phase transitions, the work done to bend the metal is converted to heat in the center of the wire. Undoing the bend then quickly cools the wire. Both of these temperature changes can be felt by hand. Shape memory and superelasticity together allow nitinol to be used in a range of applications, such as durable, bendable glasses frames and stents that are capable of expanding themselves within an artery. It is also being tested for use as airless tires for bikes and vehicles like the center image, which shows a NASA spacecraft's tire that is made of nitinol wire mesh. It can easily move on the difficult terrain of other planets without suffering long-term damage. The possibility of many other applications exists for this alloy.
If you'd like to know more about nitinol, here's a few of the videos and websites that we used for our research. We hope you found this video fascinating. Thank you so much for listening.